Alright, so last time I ended up with this answer, but I'm gonna use this random tic-tac-toe result to show you something that is nice and amazing. Alright, I saw something that happens in all the answers that we did, and it seems to be that it is just some flips and rotations and reflections of the same thing. So this is what I found out. Just move down a bit. I'm just going to copy that tic-tac-toe result down here and paste it. Alright, so that's the result now. As you can see, I would do what we call in mathematics as a quarter rotation. So if I would rotate this by 90 degrees, then what I would get is this thing right here. Let me just use yellow. This thing right here would go to the side, and obviously this thing right here would go in here, and this thing at the bottom will go to the side, and the thing on this side would go to the top. And the center, obviously, this is center. This is called a quarter rotation. Now, you notice that this quarter rotation is entirely different from the origin or the starting set, and hence these are two different ways of creating a result in the tic-tac-toe. So how about let's try to do another quarter rotation and see what we get. I'm going to use this color so I know where I want to. So this is the one on the side. The one that's underneath goes in here. The one on the side goes on top. The one on the right side and the one on the top goes on the left side. And the center is still the center, obviously. This, as we turned it into another quarter rotation, it doesn't look like any of this, and hence it is a distinct set. Alright, and let's go and try another one again and see what that leads us. The bottom goes to the side, the right side goes to the top, the top goes to the left side, the left side goes to the bottom, and obviously the center stays in the center again. Alright, is it the same as any of this? I don't think so. It's not the same, so it's another distinct rotation. Now notice if I do another one. If I do another one, obviously you know it goes back to this. So we can only do 4 quarter rotations to make a distinct set. Now, is there another way of rotating this? Yes, the answer is yes. Another way is called reflection. So we're not rotating it, we're reflecting it. So let's try to reflect this thing along the y-axis. What I meant is, Imagine that you have a y-axis passing through the center right there, and we're gonna rotate this, flip it around that. So I'm just going to use the color signature that I use here. This would be red. So if I flip it along the y-axis, it would be x, ox on the right side. The center would remain 0 on the circle x and x. And this is violet, so I'm going to use violet. So violet would be x, ox. So this is a result of flipping it on the y-axis. And as you can see, it's brilliant. It's different. Can you see something that looks like it? I don't think so. There's no XX00 on the front. I don't see it. So this is an entirely distinct set. So now imagine if I flip it on the x-axis, and I'm going to flip it here. I'm going to flip it there. So notice that I have this yellow thing, so I'll just that thing goes down. That thing goes down, I have this green thing that goes up, and the white thing remains on the center. If I'm gonna draw it, then this thing is another distinct set. As you can see, it doesn't look like any of this XX. There's no XX on the top, so it's another distinct set. Is there any other way we can reflect this? I think so. There's another way. The other way is by going in here. So going in this kind of reflection. So if I do that, then notice that the one on the exact diagonal would stay in there. So let me just put a line here. So this is a reflection. This is a reflection using the y-axis, and this is using the x-axis. This four of these other rotations is using the quarter rotation. And finally what we'll do now is, let me call it the diagonal rotation. So you see that the first diagonal rotation would leave an x0 on this diagonal, but it would flip this guy. So let me just use another color. The circle and the circle here and the circle there flips, but since it's the same, so it's just the same thing. And the one in here flips, so this one becomes a 0 and this one becomes an x. Unfortunately, this is both an x, so it just stays in there. Now let us inspect. Is there anything that looks the same as this? I don't think so. X0, no, not the same. So this is another distinct set. We're left with one more reflection to do, which is to the other diagonal. And in that case, you see that there is another XXX along the diagonal. So let's just write down XXX. And if we flip it that way, then the circle, the circle remains the same, but if you flip it that way, this 2 would interchange, this 2 would also interchange, so we would have, on here we would have a circle, we would have an x, because this and that they flip, and this circle and that x would flip, so that's an x, and a circle here, and the circle would flip, it's a circle and a circle. So is any of this other guys look the same as that? I don't see any. It's all different. So now we have 8 8 different distinct things just coming from one. So that is what we call as uh, reflections, and rotations. And all of this is under the math of group theory. And I was able to find all the distinct, basis sets that is able to do eight distinct rotations. And I would show you all of the possible uh, basis sets that I was able to make out of the result that we have.